Okay. Our next speaker is Sean Eberhard from Cambridge, who will speak on the apparent structure of dense Sidonsets. Please.
Okay. Thank you very much for the invitation. So let me say, before I say anything else, that if I say anything with content, that content is joint work with Freddie Manners from UCSD. Okay, so my title is the apparent structure of dense Seedonsets. So let me start with a definition, which I expect will be familiar to almost everyone. And it's the definition of the word apparent. So English is a strange language in which some words have multiple meanings. And it's even stranger in that sometimes the meanings are almost exact opposites of each other. And apparent is one of these words. So the first sense of the word apparent, which is used sometimes, is basically obvious. If something is apparent, then it's just totally clear. You hardly need to give a talk about it to explain it to anybody. But the second sense of the word apparent, and I want to, well, the second sense is basically not obvious. So something is apparent if it seems to be true, but we don't really know why. We can't really explain it. It just seems to be true, and maybe it's even misleading. Maybe it's not really true. It just seems to be true. So for the avoidance of doubt, what I mean when I say the apparent structure of dense Seedonsets is this second meaning. Okay, so second definition is that of a Seedonset. So Seedonsets are a pretty popular topic at this conference. I was happy to see. So a Seedonset in this talk exists in an arbitrary abelian group G. And a Seedonset S is a set where there are no solutions to x minus y equals z minus w other than the trivial ones. So when you look at the differences of all the elements in your set, those are all distinct. So what are the trivial solutions? Well, the zero difference I obviously get as many times as there are elements in my set. And obviously the other trivial solution is where I just take x to be equal to z and y to be equal to w. So those are the trivial solutions. And if there are no other solutions, then the set is called a Seedonset. So why are Seedonsets interesting? Well, Sidon was interested in them because of Fourier analysis, essentially. But I think the reason why they're still interesting after 60, 80 years or whatever it was, is that, well, the notion of an additive quadruple and additive combinatorics is very central. So it's a set with many additive quadruples is known to be highly additively structured. And so a set with no additive quadruples is sort of the polar opposite of that. You expect it to be totally unstructured. It's just, you know, whenever you need an unstructured set, you just say, okay, suppose that it's a Sidon set, and then what happens? So Sidon sets are like they are the canonical unstructured sets to use. But it's a bit of a paradox, therefore, that if you ask for a Sidon set which has nearly as large as possible size, then it seems like it has to be structured again. In all the examples we know, there's a strong algebraic structure. So that's what I want to talk about. Okay, so how large can a Sidon set be? So here's a simple lemma, and this really is apparent in the first definition of, in the sense of the first definition of the word apparent, which is just that if a Sidon set is a set in which all the differences are distinct, all those differences have to fit into the group. And so you get a basic upper bound, which says that the size of the set times the size of the set minus 1, that's the number of non-zero differences, plus 1 for 0 must be at most the size of the group. And you can solve this quadratic equation, and what it tells you is that the size of the group is at most this expression, which is essentially square root n. So size of a Sidon set is at most square root the size of the group, essentially. And the question that I want to talk about in this talk is, can we say anything if the size of the Sidon set is close to square root n? Actually, spoiler alert, I won't really be able to answer this question at all. I'm just going to sort of speculate and observe what structure is in the examples we know. Okay. So here's a poll that I would like to conduct among people who care about these things, and I think the results would be a little bit controversial. So let's just consider the cyclic group Z mod NZ, and let's find the largest Sidon set in Z mod NZ, and call its size S of n. And what I want to know is, what is the size of the ratio S of n divided by square root n? Well, we will see some examples in a moment in which this ratio is very close to 1. So the lim sup is certainly 1. That's not controversial at all. What's much more mysterious is the lim inf. So is there a sequence of integers n in which this ratio is small? So the question is this lim inf equal to 1 or is it less than 1? And what I think is that the possibility that it's equal to 1 is sort of initially more attractive, just because we have a natural upper bound. It's very difficult to make any progress on this upper bound or to say anything else. So you might speculate, well, maybe this upper bound is kind of essentially tight. And I think that guess was pretty popular for a long time. I think probably Paul Erdős would have guessed that the lim inf was equal to 1. But I think that this second possibility is much more plausible these days, partly just because it's been a long time and we still don't know many more examples of Seedonsets. So it seems like they're much rarer than we originally thought. So let's look at some data for this question. So here I've looked at all n, so we're still in the cyclic group. I've looked at all n up to size about 300. This is not my data. I've found this data on the internet. And the blue line here is the size of the largest Sidon set. And the orange line is the trivial upper bound that I wrote down a couple of slides ago. And what you can see is that occasionally we have these spikes where we attain this upper bound, but very often we don't come quite close to it. And this bottom plot is just the ratio of these two lines. So this is the ratio of this is precisely the ratio I'm interested in. And as I said, the lim sup is 1. So infinitely often it will spike up and hit 1. But it really looks like to me from this plot that the lim inf is significantly less than 1. It looks like it's no more than 0.85 or something. But even that's very unclear. Okay, so so what are the constructions of the large Sidon sets? So I'm going to call them the Desarguian constructions, and I hope to elucidate that term in due course. But there are basically 5 well-known constructions of dense Sidon sets. And when I say dense, I mean really close to square root n, like 1 minus the low 1 times square root the size of the group. And I'll just tell you what they are now. Some of them are a little bit difficult to understand at first sight, and if you are a bit confused by the definition, just ignore it. It won't really be important. And a couple of the other ones are much easier to understand and are basically just an exercise to see that it works. So the first example, and the oldest and really the best, but most difficult to understand at first sight, is the one due to Singer from 1938. And here's the example. You let the group, you take a field FQ, finite field FQ, and you look in the cubic extension FQ cubed, and you take the group to be all, you take the group to be the multiplicative group of FQ cubed quotiented by FQ, the multiplicative group of the smaller field. So that's the cyclic group of order q squared plus q plus 1. And the Sidon set is, well, you take all elements in the big field of trace 0, and you look at the image in the quotient. And the claim is that that's a Sidon set. That shouldn't be obvious at this point. The next example, which is much easier to understand at first, is well, one due to Erdős and Turan, 1941. And they just said, okay, look in FQ cross FQ and look at the graph of X squared. It's an easy exercise to check that works. And it obviously has size Q when the size of the group is Q squared. The next example is due to Bose in 1942. This is closely related to Singer's example, but this time you look in a quadratic extension, FQ squared, and you don't quotient by anything. So now you have a cyclic group of order Q squared minus 1. And the Sidon set is you take any additive quotient, sorry, you take any additive coset of FQ, which is not the identity coset. And the claim is that that's a Sidon set. Okay, the fourth example is very often attributed to Ruja, because he mentioned it in a paper in 1993, but it's actually due to Spence in 1977. And this is another quite easy to check example. So the group is, you take the Cartesian product of FQ with its multiplicative group of non-zero elements. So in other words, the group operation in this group is in the left coordinate you multiply and in the right coordinate you add. And the Sidon set is just the diagonal. Okay, in the last example, I've seen it attributed a couple of times to Sigurwello and from a paper in 2012, but it turns out it goes back all the way to Hughes in 1955. And in this example, you take FQ cross times FQ cross, so the Cartesian product of the multiplicative group of FQ with itself, and you take all elements x, y, they have to be non-zero, of course, such that x plus y equals 1. Okay, so these are the 5 standard examples, I would say. And what I want to do for the rest of this talk is essentially make sense of this slide to you. And what I could do at this point is I could go through each of these examples one by one and explain to you why they work. But instead what I will do is I will give you one general construction, prove that it works, and then I will point out how each of these 5 examples is a special case. Okay, so for my general construction, what I need is a projective plane. So most of you will probably know what a projective plane is, but in case you don't, you should look it up on Wikipedia. But it's a set of points and lines. So you have things called points, and you have things that you call lines, and you have an incidence graph that tells you when points are incident to lines. And the only rule that you must that it must satisfy is that any 2 points lie on a unique line, and any 2 lines intersect in a unique point. It's totally equivalent to think of this in terms of bipartite graphs. So you have a bipartite graph where the left vertices you call points and the right vertices you call lines, and the bipartite graph tells you what the incidences are. And then the 2 axioms are that there's no cycle of length 4, and the diameter is 2. So that's an equivalent definition. Okay, so you have a projective plane. And then you consider the automorphism group of your projective plane. So an automorphism of a projective plane is some way of moving around the points and some way of moving around the lines in such a way that you preserve all incidences. Okay, so that's a group. And then what I need for this construction is I need an abelian subgroup of the automorphism group. So call that G. That's going to be our group. And then finally, I need a point with trivial stabilizer and a line with trivial stabilizer. So in other words, if you look at the orbit of this point, the group acts regularly on that orbit. And similarly, the group acts regularly on the line. And you should think of the point orbit and the line orbit as both being very large. So almost all the points are in a single G orbit, regular G orbit. And similarly for the lines. And then the Sidon set is just this sort of point line stabilizer. It's all elements of the group which keep the point on the line. Okay, so that's the construction, and let me prove to you that this is a Sidon set. It's basically just a definition chase. Okay, so I emphasize that the group G is abelian, but somehow in the context of the proof, I mean, these elements, the elements of G are automorphisms, so it just makes more sense to use multiplicative notation. So I'm going to use multiplicative notation. So an additive quadruple is a set of elements x, y, z, w in the set S, such that x inverse y equals w inverse z. So let's look at the point Q, which is the image of P under this common ratio. So Q is equal to x inverse y applied to P, which is the same as w inverse z applied to P. Then the main claim is that the points P and Q lie on the lines x inverse L and w inverse L. So there are 4 claims there. So let's just check them. So why is the point P on these 2 lines? That's just the definition of the set S. So x and w are in the set S, which means that P is contained in x inverse L and w inverse L. Why is the point Q contained in these 2 lines? Well, y and z are in the set S. So that if you chase that through, it just says that Q is contained in x inverse L and w inverse L. Okay, so now we have a pair of points and a pair of lines such that both points lie on both lines. And that's not allowed in a projective plane unless the 2 points are equal or the 2 lines are equal. So either P equals Q or x inverse L equals w inverse L. And finally, I'm assuming that the action of the group on the orbit of P and on the orbit of L is regular. So what that implies is that x equals y or x equals w. So it's just a definition chase to verify that the set S is a Sidon set. Okay. So the other thing that we need to think about is, okay, so it's a Sidon set. It's not difficult to construct Sidon sets if you don't care about their size. So what we should also think about is how big is the set S? And I won't go through any details for you, but it's easy to check that if your group G is large, if you have a large abelian subgroup of the automorphism group, and by large, I mean it has size 1 minus little o 1 times the number of points, then the Sidon set S is also a dense Sidon set. So if almost all the points are in the big G orbit, and similarly almost all the lines are in a single line orbit, then this is a dense Sidon set. Okay, so I want to apply this proposition. So what I need to do is I need to pick a projective plane, and I need to pick an abelian group of automorphisms. And the projective plane that I will use is just the standard, what is called the Desarguian projective plane. It's called Desarguian because it satisfies the theorem of Desargues. And conversely, if a projective plane satisfies the theorem of Desargues, then it has this form. So it's the standard projective plane. So you take a finite field FQ, you look at the 3-dimensional vector space over FQ, and you look at all the lines in that vector space. So that's the sort of standard projective plane. And well, the automorphism group of this projective plane is isomorphic to PGL3Q, semi-direct product with the Galois group, but please just ignore the Galois group for now. It's not really important. So PGL3Q is it's the group of 3 by 3 matrices over FQ modulo scalars. So that's the projective plane we'll use. And now we need an abelian subgroup of PGL3Q. And you can actually just list the maximal abelian subgroups of PGL3Q up to conjugacy. And here they are. So, so there are a couple of very big cyclic subgroups of PGL3Q. So how do you get a cyclic group? You choose a matrix and you see what group it generates. So if you look at a matrix, you can look at its eigenvalues. And those eigenvalues will be in FQ or FQ squared or FQ cubed. So if you have an eigenvalue which has degree 3, then they all have degree 3. And it's possible that the eigenvalue is a generator of FQ cubed. And if that's true, then the element generates a cyclic group of order q squared plus q plus 1. That's a so-called Singer subgroup. The second thing that could happen is that you have one eigenvalue of degree 2. No, you have one eigenvalue of degree 1 and 2 eigenvalues of degree 2. And if your eigenvalue of degree 2 generates the multiplicative group of FQ squared, then you get a cyclic group of order q squared minus 1. I guess that deserves to be called a Bose subgroup, but nobody calls it that. Finally, there are a few other abelian subgroups consisting of upper triangular matrices, which I've listed here. And okay, so for each of these abelian subgroups, we can plug it into our construction and we can see what Seedonset comes out. And I can leave the details to you because it's just sort of checking and changing coordinates a bit, but this is the correspondence. So in this first case, you get Singer's example. In the second case, you get Bose's example. You get, and so on. Finally, there are a few other maximal abelian subgroups that I haven't listed here, but they aren't relevant. Either they're too small to go into this construction, or there's no large point orbit, or there's no line, or there's no large line orbit. And finally, that's it. So you can just check that that no other constructions arise in this way. Okay, so what about other projective planes? There are projective planes other than the Desarguian ones. They're called non-Desarguian projective planes. I won't get too much into the details, but there are other Seedonsets that arise from non-Desarguian projective planes. So let me just give you a few examples. And all examples I know have the following form. You take a function from FQ to FQ, and that function is called a planar function if, when you look at the graph of that function in FQ cross FQ, that's a Seedonset. It's also called a perfect nonlinear function in the computer science literature. So these things are quite well studied. So we saw an example of this form earlier. If you just take phi to be x squared, this gives you the Erdős-Turan example of a Seedonset. But it turns out that phi does not have to be quadratic. So so one example is due to Dembowski and Ostrom from 1968, where suppose x is a power of p to the d, then what you can look at is x to the p to the e plus 1 for some other e. And there's some condition that I've listed here, but this works. But you could argue that this is still kind of basically quadratic. Here's another example that was written down by Coulter and Matthews. And this one's more interesting because it's not monomial. You take x to the 10 plus x to the 6 minus x squared over a field of characteristic 3. And again, this works. But you could still argue that this is kind of morally quadratic because each of these exponents is a sum of 2 powers of 3. So this is 9 plus 1, this is 3 plus 3, and this is 1 plus 1. And I agree with you. That is basically quadratic. But here's another example. You could take, again, a field of characteristic 3, and you could look at x to the 3 to the e plus 1 over 2. And that over 2 part really makes this a very different example. It's a really surprising example, again, of Coulter and Matthews in 1997. Okay, then in my last minute, let me just say what we think may be true, at least judging from just these examples. It may be true that if you have a Sidon set S, an arbitrary group G of order n, and if it's dense, so if it has size 1 minus little o 1 times square root n, then for all we know, it is true that G acts on a projective plane and S is contained in this point line stabilizer. So we don't know any counterexamples to this conjecture, and that's really remarkable if true. But as I said, we have no idea how to prove this, and maybe it's just completely illusory. Maybe we're just not good at constructing Sidon sets as a field. So here's a sort of baby case of this conjecture that we still have no idea how to solve. You take the group to be FP cross FP, and you say, suppose I have a Sidon set S of size P, then the conjecture is that S must be a parabola. So this is known to be true if S is the graph of a function. So if it has the form x comma 5x as x ranges over FP, or if it satisfies a sort of vertical line condition, then it's true that S must be a parabola. But once you omit this vertical line condition, it's totally unclear. Okay, so I think I'll just stop there.
So, Sean, thank you very much. It was actually, for me at least, a fantastically interesting talk. And I've been trying to get people to think about projective planes for a while, and this will be maybe further impetus to do so. We have time maybe for 1 or 2 questions. So I am looking at the Q&A and so there's a question from Jae-Woo Lee. For those graph examples, are they dense?
Yes. So yeah, so I didn't mention that, but that's certainly true. So in these examples, I'm taking S to be the graph of a function phi. The group G is FQ cross FQ, and the size of the set S is clearly exactly Q, because X is allowed to range over the whole x-axis. So yeah, these have size exactly square root the size of the group.
And one last question from David Bloom. What about large subsets of the integers from 1 to n? Do you conjecture a strong link with projective planes there also?
Certainly that's true of all the examples we know. So yes, I would suppose that might be true. But again, I hasten to add that these are sort of apparent conjectures. Like there's no really good reason to believe these things other than we just don't have any other examples. But maybe that's the only reason ever to conjecture something. I don't know. Anyways.
So again, Sean, thank you very much. And our next talk will be in 2 minutes.